Now better. Okay. Yeah, then basically a bit about me. I'm working at BMW in Munich. I work on C++ for quite some time now and in safety critical systems since 2018. And I represent BMW at the MISRA C++ working group and also in the ISO committee meetings. But what I would like to know is a bit about you before we start. And let's try to have a raise of hands. How many of you are not allowed to use dynamic memory allocation? 1, 2, 3. Half a bit. Okay. How many of you do not know what are the issues of dynamic memory allocation? Okay, one that do not know. Most of the people know about the issues. Okay, let's see if that is the case after the talk, if you still believe that you knew all of them before we started. Okay, in my area we talk about safety critical systems, but first we need to define what is a safety critical system. It's a system whose failure could lead to loss of life or serious injuries. It could lead to significant property damages, or could lead to significant environmental damages. And as an example, we could have a nuclear power plant in Italy that it's now out of, not working anymore. We have this nice, cute plane that to transport planes, a kind of a planeception, I guess. And we have this X-ray machine. All of them would be examples of safety critical systems. And when it comes to safety critical systems, you will hear a lot about functional safety. There has been a lot of discussions in C++, also in other languages about safety. What does it mean, safety? Some people talk about memory safety, some people talk about functional safety. And here we'll focus about functional safety, because that is in the end what we care about. And what is functional safety? The goal is to protect the user from technology. That would be like having said in a short way. In a longer way, it's the system that lead to the freedom from an acceptable risk of injury, damage to the health of people by proper implementation of one or more automatic protection functions, also called like these safety functions. And a safety system is one that consists with one or multiple safety functions. But let's grab an example. You all probably have at home a kettle, and the kettle, you like it or not, or you know it or not, it has some safety functions there. It has an automatic switch off. Usually you boil the water, and then at some point it just automatically turns off. This is to protect from burning risk. It has a boil dry protection usually, like if it runs out of water, it will just stop also to prevent from fire hazards. And it also has usually some pouring, like some protection that when you pour water, you don't have a splashing and you could burn yourself. And all of this is like, it's the part of functional like safety that we have. And if you see here, there's nothing about is the kettle running in Java or in C# or in Python. We don't care, we are a user. I don't care what is inside, as long as I'm safe on using it. And that is functional safety. Now, this is regulated, it's a sector that is heavily regulated. You want to make sure that the things are fine. And we have one standard to rule them all. That is this one. And if you don't have a better standard, that is the one that you can use. But then we have a standard for different domains. We have industry, nuclear power plants, medical devices, so on, so on. The one that I'm more familiar and I use is the automotive, the ISO 26262. This is the standard that regulates automotive regarding safety. And this is to understand where we are coming from. Okay, it's a regulated environment, we have this standard. Now let's take a look what the standard says about that. In the standard, like you have, the first thing that you have to do is to define how critical that is. It's not the same a nuclear power plant that just a single car, or you have different levels. And basically like in automotive, also like inside automotive, you have different levels and you have several categories. One is the severity, like if something happens, how bad it is. Will you just, it's uncomfort, is it really you lose the arm, whatever. You have exposure, how often are you exposed to that certain issue? And then you have controllability. If something goes wrong, how easy or hard is for the user to do something about to control it. Based on these 3 dimensions, we can draw a matrix, and then here where it enters the topic about ASIL levels that maybe some of you have heard about. It goes from ASIL D, that is the most critical scenario that we have here in the lower right, and then you have the one that's like less critical, that would be the QM. And this is part of the standard. And then during the standard, when you read it, you end up finding some kind of tables that tells you things that you should consider, that are recommended or strongly recommended. And this is a typical table that you would find on this standard. And it tells you, depends on these categories, A, B, C, or D. And you have some entries, and it tells you like, okay, is this highly recommended? Is it just recommended? Or it's not recommended, but not against, like do whatever you want with that. And this means that what the takeaway here, it's more that depends on the criticality, you are more or less restricted. But now let's go to the content. If we go to the content, this standard has 12 parts, it's super long. If you are interested, just grab part 6, it's the one about software development. You have parts for hardware also. And then we start, and we have some general topic for software development. And then we start seeing like the first point, that here like it requires the use of coding guidelines. And this is like, okay, now we have to use coding guidelines. We have a regulation telling us that. And what these coding guidelines do, use of language subsets that exclude like certain constructs that might be interpreted differently. Doesn't mean that they are wrong, but like if you have an idea of what it's doing and you have another idea, maybe that's not a good thing to have. Also could be a construct that experience tell us, hey, this might lead to issues. Or you have certain constructs that you know typically that this can lead to unhandled runtime errors. If we move a bit farther, we have a section, software architectural design, and then we talk about appropriate management of shared resources. Okay, we need to take care of shared resources, and memory is a shared resource in our system. When we go to software unit design and implementation, what we want to do is like we want to achieve correct order of execution, correctness on data and control flow. And to do that, now here we start seeing no dynamic objects or variables. Or if you do it, like a test during the creation. Also tells you about avoid global variables or justify their usage. And also talks about no hidden data flow or control flow. And this is what we have in this standard. And this is what we have to follow. If we want to get certification, if we want to put our car on the road, we need to follow that. And now it comes on how we implement. Okay, we have guidelines. Which guidelines we have available on the market that could be useful for us. We have the Joint Strike Fighter coding guidelines developed by Bjorn quite a long time ago. Then we have the AutoSAR guidelines. These some guidelines that were done for in the context of automotive industry to program in C++14. And then we have the new MISRA C++ guidelines that were released on 2023 to program with C++17. And what all these guidelines have in common is that there's a point that says do not use dynamic memory allocation. Okay. But they go a little bit farther. Like, do not use dynamic memory allocation after initialization phase. It's not the same to have a bug or an issue when you are starting a car, or if you are driving at 220 kilometers per hour on the highway. Yeah, we can do that in Germany. I know that here there are some speed limits. And basically then also like, if you have to, if you still need it, because realistically nowadays in big systems we need to do that, it provides you some guidelines. And basically what these guidelines wants to avoid are the following issues. One is we want to avoid memory leaks, because we don't want to run out of memory. If we have memory leaks, at some point we might run out of memory. We also want to avoid allocation, deallocation mismatches. This is something that we'll see a little bit further later. We also avoid memory fragmentation, and mainly we want to avoid memory fragmentation because we also want to have we want to avoid to have non-deterministic runtime. This in some systems that is important. And the other situation that we want to avoid is the use after free. Okay, now we saw a little bit like where we come from. We saw like the regulation, the ISO, and the guidelines. But now let's take a step back and let's go from the other end, from the code, from the programs that we want to run. I wanted to try to find a definition of a program. I found nothing that I was satisfied about, and I came up with this. And to me, a program is nothing else than a bunch of instructions modifying chunks of memory. Based on some inputs, you produce some output. Basically, you have your computer, and you have instructions inside, you have memory, you provide inputs, you get output. That's it. That's nothing else than that. That's what a computer is doing. Now, how we reach to that point? Basically, we have a bunch of source files. My presentation is based on C++, but it could apply to some other languages as well. Basically, we have a bunch of CPP and header files. We provide it to some compiler, and then each translation unit gets compiled. We produce an object file, goes to the linker, and then from the linker, we create an executable, and now we have an executable. Now this executable, what we want to do is we want to do something with it, we want to start it, we want to run it, and usually you have it in the machine, completely stopped. Now you want to start it, and what it happens in the moment that you want to start it, usually you have some implicit loading of dynamic libraries, and then after starting, you still go into some running state, and once you have it running, you can still explicitly load additional dynamic libraries. That's in general how the workflow of a program works. Okay. During the talk, I have some examples on GitHub that you can find. For each example, you have the QR code, and you can find them all later, play around. I will not do it live. We will not risk on that. I have here the screenshots. Let's just start first on trying to take a look to the ELF format. Basically, here we have a program, quite simple, just return 0, but has a bunch of variables. Can you see it proper at the back? Good. Okay, basically once you have your binary that is compiled, you can use the read elf binary, and if you run it with ---- sections, you will see that this binary is composed of several sections. And you will get this, this list here. In this list, you can see like some section name, and then basically you will see some addresses where this section is located inside the binary. Just remember, for now we did not start it. This is a static binary. And then basically you have also the size of the section, and then you have some flags. That these flags, they have, if this is a section for executable or read, what is the nature of the section. And here on the below, you can find the explanation of the different flags. But here we don't have any information about the variables that we have defined in our program. And the interesting part comes next, when you have this, you can run readf with ---- symbols, and this allows you to figure out what symbols you have in your binary and where they are located. When you do that, you see here this column with name, and here you see the bunch of symbols that your program contains. And here you have some mangling going on. And if you look, for example, at the lower lines, 11, 12, 13, 14, these are the variable names. You just need to remove the underscore ZL, that's part of the mangling. But these are the symbols that we have in our program. And here you can see where these symbols are located into the binary. You also have this column that it gives you like in which section it is. This number here, it's an index to the slide that we saw before. And now to just do the mapping, I just do it for you. And basically what it means is that when we have this program on the left, what we have is that this part goes into the data read-only. Then we have this part that is like variables that are uninitialized, non-constant. They go to the BSS section. This one goes to the data section. This one goes to the read-only data section. And the instructions goes into the text. And this is how your code ends up into the binary. Now we have the binary, and now we want to run it in the machine. And when we want to run in the machine, the first thing is that we do is we need to load the program into memory. It needs to live somewhere. You cannot just execute directly from disk. And the first two sections, they end up in this memory segment, and then you have the other three that end up in another memory segment. You can see that one is for you see this Rx, is because it's read executable, it's the permissions. The second one is like a read-write section. But then you have also other segments, memory segments going on. You have these two, the VVAR and VDSO. These are for communication with the operating system. We will not talk about them. Then we have a segment that basically it's a dynamic library that is loaded. That basically is like it's the loader to load dynamic libraries. You will have to load dynamic libraries, and you need some piece of code for that. And now here comes the stack. Like here's where we have a memory segment where we'll have our stack, and we'll be creating all our local variables. And this is on the starting phase. But now we saw that there's a starting phase, and then you go to the running phase. And when we go to the running phase, this section gets divided in two. Not really much relevant for this talk. But now here, some additional dynamic libraries get loaded. In this case, this is the standard library. And then we have a new section appearing, that is the heap. And this is where will happen our dynamic memory allocation. And the heap grows. This section will grow in this direction, and the stack will grow in this other direction. Okay. Now let's see how the stack grows. We saw that we have a section that is the stack, and there's this program, this example. Can someone tell me what this is doing? Basically, it asks you for a number, you provide a number, and it returns you the same number, calculating it in a recursive way, in a pretty dumb way, that basically you just sum one as many times as the number you provided. Like it's probably the most stupid recursive function that you can ever create. But basically you will have a stack that is as deep as the number that you provided, basically. Now, basically, once you if you run the program, and you run it, for example, with GDB, and you stop at the first instruction, you can do these info proc mappings, and you will see how it looks like in memory. These memory segments that we have talked about, you can just see them here clear. And what you see is that you have here the stack, and that's, for this example, is the part that we want to focus. And here we can see the size in hexadecimal, basically these 132 kilobytes of memory. Okay, now we have this program. What we want to do is that we put a breakpoint on the return 0. That would be like the deepest when the moment that the recursivity ends and you want to start unwinding. And we ask for a number to be computed. In this case, 20,000. This will be a stack trace of 20,000 calls approx. And basically then we check again, and we see that the data segment for the memory segment for the stack, it grew, and it's 632 kilobytes. Now what do we do is that here we have a loop, we continue, and we ask again, and we say, okay, which number you want to compute? I want to compute 0. And now basically like we already unbound all of that. Now the question is like, how will be the stack? The size of the stack? It's exactly the same. Because the stack, one issue that it has is that it will grow, but it never shrinks. Not sure if it surprises you, but that's how it is. Now let's go to take a look to the heap. Maybe the heap is simpler, harder. Let's see. This application, what it does is that the first thing that it does is to search in a programmatic way for different memory segments, and it prints the segment that is regarding to the heap. Like when it finds that it's called heap, it goes there and it prints this part, and now it tells you, hey, what do you want to do? And you can just allocate memory, deallocate memory, and so on. And this is nothing else than doing a make unique of an array, and that's it. Let's see what it happens. Okay, we start with this heap, and now we say, okay, the heap by default started with 135,000 bytes, and we said we want to allocate 50,000 bytes. Okay, that should fit. Okay, we already see that now the heap grew. Now the heap is at 270,000 bytes. Not sure why. I mean, it was fitting there. We didn't allocate anything. Maybe someone else was already using the heap. Fair enough, that could be. Okay, then the heap now it's growing to allocate more memory. Okay, now let's go a bit wilder. Let's try to allocate 100,000 bytes. Okay, it means that it's 150,000 until now. We stayed the same. It's 270,000, didn't change. It seems that all of this data was able to fit into the current heap. Okay, wilder. Let's allocate 200,000 bytes. And now what we see, wait a second. The size of the heap did not change. We have allocated so far 350,000 bytes, but the heap stays the same, 270,000 bytes. How this can happen? What's going on here? Okay, someone heard about, or we heard about the concept of lazy allocation. Maybe someone heard about that. Maybe that's the case. I don't know. Let's try it out. One option that we have here is that we can touch every single piece of memory. I created this option. That basically what it does is that all the memory that we allocated, we just write to it, whatever, something. With this way, we make sure that it gets touched. Nothing changes. The heap stays the same size. What's going on then? Okay, let's print we have this option here that you can print the address of the pointers. And if we do that, what we see is that the first two allocations, here what you can see is the beginning is like, okay, how many bytes the chunk set of bytes that we wanted to allocate. We allocated 50,000 bytes, it's at this address 0x55. The 100,000 bytes, it's 0x55. But now we see that these 200,000 bytes, it's in some completely different address. Okay, it's like, it seems that, where's this going? And now let's see what's happening. When, as I said, I create these allocations through make unique. And when you do make unique, what it happens is that under the hood it calls new. And new, what it does is that under the hood calls malloc. And malloc, what it does, well, it depends. It could be that ends up in a system call or not. It could be that doesn't have to do a system call because you have a heap that fits there, perfect. You have an option that you can, it calls VRK, that basically this is the instruction that once you have a memory region, it can expand it. That's what we saw when it was growing. Or the third option, that it could be that do a new call to mmap. And basically what it does is like, it's just requesting another memory segment for this dynamically memory allocated. And unless that you are quite deep onto that, to me it's a bit surprising. And what's going on here? Well, the behavior depends on the implementation. This is nothing that is defined on the standard. And if we check like the glibc, here I put you the link where you can go. It's really a nice reading before going to sleep. And basically you have, in reality you have multiple heaps. It's not, if we think about that the heap is the memory region, you can have multiple ones. And you have a linked list, and depends on the size, it goes in one or the other one. It's just more complicated than just one memory segment. And with that, it's like I just want to show you this part of complexity that comes there that doesn't depend on us. And this is only the software part. What happens with the hardware? Well, in the hardware, we have multiple cores. These cores have some registers. And the register, they have some different cache levels. We have then the RAM memory and the disk. And this memory could be that when you want to access the memory, maybe it's in the register, maybe it's in the cache. And each of them has a different cost for accessing. Like if the L1 cache data takes 1, the L2 would take 4 times more, the L3 would take 40 times more, the RAM would take 80 times more, and the disk would take 10,000 times more. And this then like the part that, if we remember, one of the issues that we wanted to avoid, that was like the non-deterministic runtime, this make it harder to know like, okay, how long it will take until we get our data. And this comes from the practice part. This is what we have in the code. But what is it in the standard? When it comes to C++, what is if all of this is not in the standard, what is in the standard? Well, the standard in C++ only knows about an object and a storage. And basically, this is something that's important to differentiate, like the two things, they don't necessarily go together. But basically, you have a storage, and this storage has some start of lifetime and end of lifetime. Usually, they might go together with the object lifetime, but you can have a start of the storage, then you can construct something on this storage. The constructor gets called. Once the constructor ends, the object lifetime starts, and this object lifetime continues until the structure gets called. In the moment that the structure gets called, the object lifetime ends. You are still executing the structure, and then you finish executing the structure, and that would be it. This would be like one simple case. You have also situations where you can say, okay, I want to reuse the same storage, and I have two objects. Like first in the same storage, first I put one object, then it gets destroyed, and then another object goes there. You have another situation where you can say, okay, the constructor starts, you start an object, and now you can start the lifetime of another object without calling the structure, and that's probably not what you want, but it's perfectly legal C++. That's totally fine. Probably not what you want. But this is what it's defined in C++. And then we also have like different types of storage. Like we have the static storage duration, we have the thread storage duration, we have automatic storage duration, and we have the dynamic storage duration. With a small exception with the small exceptions that exceptions work different, but we'll not go too much into that topic. And now if we want to map what the standard defines with what we saw before, we can do a mapping, and we see that when we saw this program loaded into memory, this part is the static storage duration, This part is the stack is the part of the automatic storage duration, and then we have the heap that is the part of the dynamic storage duration. And basically now how can we allocate? How we can do this dynamic memory allocation? That's the focus of the talk today. We can use new and delete expressions that can be used. How many forms of new operator are available? How many operator news you have in C++? Can someone say it? Some wild guess. Two. Okay, 8. And they are 4 and duplicated for arrays. And for delete, also 8 maybe? No, there are even 12. You have a lot of ways to do that. And they are all replaceable. Replaceable means that the implementation provides you one, and you can just provide your own implementation, and this will be replaced at link time. Then this is these are the form of the new and delete expression. And basically what we have is that let's take a look to the parameters that we can provide to the new, or that gets provided, because basically this is the one that you implemented and it gets called. The first one is the number of bytes to be allocated. This is something that you don't specify, but when you get the call, it gets provided. The alignment of the storage, how it should be aligned. And then basically this tag parameter that basically is to know if that should throw or not in case that the allocation fail or not. These are the three options of what the parameters are doing. Now, if we want to allocate an integer in the heap, what can we do? New int, simple, you can provide a value or not. And you just then call delete. If you want to do it with an array, you can just put it with bounds or unbounded with initialize. And you need to make sure that you call the delete also with the brackets, otherwise you have a mismatch. If you want to do it for a class, that's more or less the same. It's just instead of the int, you put the name of the class, and that's it. That would be a way that you can allocate objects into the heap. And basically all of these, they throw a bad alloc when there is not enough memory. If you do it like that, that's what it happens. Now, if we have this code and we have these 4 options of new that you could implement, which of the new version is selected here? One, two, three, or 4, or multiple, or which ones? Any of the first 2. It could be that it gets selected the one with a line or the one without a line. And which delete version is then selected? It could be any of these 4. Okay. Now, we saw that some of the overloads, it has this option about non-throwing. Then it's probably obvious that we have a way to allocate, making sure that doesn't throw if there's no enough memory. For that, we need to use the placement new syntax. And basically here what we do is that we can add this, when we do the new, we can add this to no throw. And basically what it does is that in case that if not enough memory, this will not throw. And now the question is which version gets selected when you call that. Well, basically any of the 2 below. And it follows the same pattern, basically it could be that it's the one with a line or not. It selects the one with the no throw. That makes sense. But you don't know if it will be, the align will be provided or not. Because this is the one that basically it's kind of default alignment. And what happens if we want to deallocate with new without throwing? Like we allocated with the no throw, and now we want to deallocate. We call this, and which one will get selected? Well, not the ones with the no throw, because this doesn't have an idea that this is about no throw. Like this can be in a completely different part of the process. Like you do not know that that initial data was allocated with the no throw part. And then you would wonder why this is available then. Well, it's some corner case, then this gets executed, but we'll not go into that. There's no placement new version for the delete with the no throw. Okay, but now you have also the option to choose the alignment when you want to allocate something. And how you do that is like you can provide one option would be like, okay, let's use the placement new, and we just add here a line val of 64. And the question is, can we do that? I don't know, let's ask the compilers. That's usually a good thing to do. Okay, GCC says, yeah, sure, no problem. Clang says, yeah, sure. And MSBC says, no, that's not a good idea. Okay, who is right here? Basically, it gives us this error, and it's something like, it talks about like, that it would be chosen as placement the location function. Basically, it's kind of a mismatch that it would not be able to choose the right one. Okay, what this mean? Let's see. Well, basically, like, sorry, here, I think this one I have it. Yeah, basically, what here happens is like, which one gets selected? When we do the new, it gets selected with the one with the alignment. Okay, perfect, that's what we wanted. But now if we call the delete, it doesn't get selected with the one that the alignment is provided. That's kind of a mismatch. And similar to what we saw with the throw, like you don't have that information. You don't have the information on the throw that was having the alignment. And then basically like we could say, okay, but I want to combine alignment and no throw. I want to have both. You could do something like that. And in this case, now all the compilers are happy, but still, this is just wrong. That's not the way to do it. Now, okay, then how can we do the allocating with alignment? Well, the right way to do it is that you put it on the type. If you want to have a class that needs to be aligned, you just, when you define the class, you say, okay, this class foo needs to be aligned to 64, and then basically like you just use the normal new. And then this will make sure that it calls the right new and the right delete. And here the same for the no throw. Basically like this is part of the type, the alignment, and then you can just go with the no throw. Okay, and now how many options we have to dynamically allocate memory? What other options we have? Okay, we saw the new, but what about the library? In the library, we can use the C++ is based on C. You have the C API available. You could just call the malloc functions and the free. That's another option that you can do to allocate. You can also use the smart pointers. If you start using the smart pointers, make unique, make sure this will also allocate memory. It makes sense. You want to allocate something on the heap. And in C++26, hopefully will come. It's already in the draft. This indirect and polymorphic, basically this is nothing else than a mechanism to allocate something on the heap, but still have value semantics. This is something that if you want to have the value semantics without the pointer, but still you want to have it on the heap, that's something that got introduced recently into the draft of the standard and should come on C++26. Okay, now to see like how much it's your knowledge on allocations, we'll play a game. The game is called, does it dynamically allocate memory and how much? Let's start with an easy one. Make unique, does it allocate? How much? Yes, and 4 bytes. Make share, does it allocate? Yes. How much? a bit more, 24. There's a control block there. A string, quite small string. Does it allocate?
Probably
No. Depends. I mean, at least in my machine, I'm telling you what is happening on my machine. Maybe in your machine is different. What about this string that doesn't fit onto the screen? Does it allocate? Yes, it allocates 62 bytes. What about this big string view that doesn't fit into the string, into the screen? No, because it's into the constant data that gets embedded into the binary. And a std array, does it allocate? No. A std vector, an empty default constructor std vector. No, at least not in my machine. Std vector with some values there. Yes. Okay, we have here a std function. We have this function that gives us the answer to life and everything. And we assign it to std function. We create a std function with that. Does it allocate? Someone heard, no, there's no need here. Now we have a little bit more elaborated std function where you have this, you want to bind. Does it allocate? Here, yes, now it allocates. Creating a thread. Yes, it allocates. Probably the least of your issues, the allocation. JThread. Does it allocate? I heard that it's better JThread. Maybe it does not. Yes, it allocates still. And in this case, it's 2 allocations, not 1. Std promise. Yes, and 2 allocations also. What about getting the feature from a promise and constructing the feature? No. What about setting the value on a promise? No. What about constructing the feature? No, at least not on my implementation or my machine. What about std any? Also not. What about a std any that has a small string inside? Yes, it allocates. I'm not sure if you are aware of a stack trace. It's a cool feature on C++23, I think. And it gives you the current stack trace. Does it allocate? Yes, quite a bit, 512 bytes. Okay, now the question is like, how do you know if something allocates? Because if someone tells you like, are you using dynamic memory allocation? Do you know if you are using dynamic memory allocation? Well, you have different ways. Like if you have some class, you can go to CPP reference and you find a class that says, class satisfies allocation aware container. That's probably a sign that it allocates. You will have, for example, this case for vector, and you can see that here. You have another option on the documentation. You see, okay, there's one template parameter that it's called allocator. In this case, for example, in the regex match, it has this allocation parameter here. Then probably also means that it allocates. You can provide your allocator here. What other way you have to figure out? Well, you have some functions where, if you go to CPP reference, it says, hey, exceptions. It might throw a bat alloc if memory could not be allocated. Well, that's a sign that you know that if it can throw the exception, it means that probably it allocates without throwing the exception. What other options we have? You know that the only way to implement that is with dynamic memory allocation. If you really went hands-on and you say, hey, I know that to implement that library feature, you can only do it with dynamic memory allocation, then, okay, you have privileged knowledge on that. You have another option that is you kind of try to introspect it. And that's exactly what I did in this example. You can download it, you can play around. You just overload the operator new and delete, and you see if it gets called or not. That's also a way to figure out that, except for exceptions that go with a special mechanism. Okay, and now basically the last part that we have is let's go a bit on the different mechanisms that we have to customize dynamic memory allocation. We have this global new and delete that you can replace. This is something that you could, for example, do. You create an operator new and you decide what this does, and you just implement it. You need to follow certain requirements, like you should throw if it cannot allocate, and so on and so on. But this is the first option that you have to configure that. The problem of that is that you have one new and delete to rule them all. Everything that dynamically allocates, it will go through this function. And what is very important here is that if you define one, you need to define them all. We saw, I think it was 8 new and 12 delete. If you define one, you define them all, and you define them with exact same semantics. Because as we saw, like, it's hard to figure out which one get called. Just make sure that they do the same in a sensitive way. And it replaces the default. Means that once you replace it, you have no way to access the original operator new anymore. And yeah, if you don't follow the semantics that the standard requires, then you haven't defined behavior. We have another mechanism, not so well known, that it's basically you can create a class, new and delete per class. Basically, we can have our class foo, and in your class foo, you can define a member function, new, and a member function delete, where this new and delete will get called every time that you want to create, dynamically allocate this foo, basically. This is another way that you can do it. You have then this custom allocator per type. But of course, it means that all instances of this type that you want to create on the heap, they will go through this single allocator. And of course, it's only called when the object gets created on the heap, not on the stack. Like, just forget about trying to do some global increment to figure out how many instances you have of that. No, because this only gets called when you create it on the heap. It does not propagate to members. This means that if this class foo would have an stud vector inside, and you want to then, like, this vector also needs to get dynamically allocated, this would not propagate. You are only like, it's only for this class foo itself. What other option we have? We have custom allocator. This was introduced 11? No, even before, I think, quite some time ago. And basically how it works is that you can define this a class that it's a allocator, and you need to provide certain traits, and basically you can then provide it to the different classes. And it needs to follow the allocator requirements. You have certain requirements. For example, it's mandated that you need to implement this allocate function. You need to implement the deallocate function with certain semantics. You have to follow that. Several are optional, and you don't have to implement them. The default might be good for you. And basically, they are provided through all these allocator traits. And basically, like, when you copy or move a class that has this allocator, then you have, you can specify if you want the allocator to get propagated or not on the copy or on the moving. That one is the one that we had until, recently. What we got in C++ 17 is polymorphic allocators, PMR. That's quite much more neat. And here what we have is that it's, I think it's much more user-friendly, and also to read from the read point of view, I think it's much simpler. You can just, here on the right at the top, we define some storage. It's an array of bytes. And then basically you can just, this memory resource, you define this memory resource, and in this case it's a monotonic buffer. Basically, history have tell us that when people come up with custom allocators, usually you end up implementing 2-3 different types of custom allocators. There are like not so many. There are some of them that's you have the approach that, for example, you allocate and you never deallocate. But basically you have 3 or 4 that are the most common ones. And they are already provided. And one of them is this monotonic buffer resource. And then here you can just provide the storage to this resource. You have also this option here that you can provide a kind of a fallback. Like you have a memory resource, and it's like, if this would run out of memory, what do I do? And you can say, okay, go to fallback to this other resource. In this case, we have the null memory resource, that is to say, okay, just abort, like if it runs out, it's like it terminates. And then when you define the vector, you can just provide your memory resource. And the vectors are under this astute PMR vector, basically. Basically, the allocation can be configured at runtime. As you see now, here you could provide different, compared to the previous one, that was a template parameter. Here you can just provide the resource at runtime. And functionality is divided between this polymorphic allocator and the memory resource. And that's like the good separation. The standard library provides multiple memory resources. You can always create your own if you have some complex scenario, but a lot of times it could be that one of them is enough for you. And it includes this null memory resource, that basically like this null memory resource, if you try to allocate with it, it just terminates. That's it. It's a way to kind of guarantee that there's no allocation happening. And you also have, it also provides the classical new and delete memory resource. You can explicitly say, hey, this is the memory resource, and it will just do the global new and delete. They do not propagate on move copy assignment. And maybe one of the biggest issues is that if you swap 2 containers, and these containers, the allocator, they do not compare equal, that for allocators to compare equal means that if you allocate with this allocator, you are able to deallocate with another allocator. That means to compare equal. If they do not compare equal, then that isn't defined behavior. That's something that to be careful. But it does propagate to the members. I think that we saw that before was not the case. Yeah, basically with that we reached the end, and I want to just summarize a bit what we saw here. The end goal, and that's the part that we should not forget. Let's go back to the beginning. The end goal is to provide functional safety. We want that someone doesn't get killed when driving a car. So we want that someone does not get burned when using the kettle, and so on. That's the end goal that we have here. The C++ mental model is one part, but the implementation plays a big role. You need to know your implementation. The OS, how it behaves, the standard library, the compiler. There are a lot of factors there that if you use dynamic memory allocation, you need to know. And when using allocators, you should remember what you want to solve, because you can end up creating your own allocator. Sure, you are not using the heap, but you created there such a complex algorithm that maybe it's still non-deterministic runtime. Or you might end up with out of memory, or you might end up with memory fragmentation. I mean, in the end, it's like the global new one delete, it's someone that tried to implement a general purpose allocator. But if you end up over-engineering your allocator, you will end up exactly with the same implementation. And that's why you need to keep in mind, you want to avoid memory leaks, you want to avoid out of memory, allocation, deallocation mismatch, memory fragmentation, non-deterministic runtime, and the use after free. And with that, I reached the end of the talk. I hope that, I don't know if right now, like, you believe that you knew all the issues before you started or not. It's not about scaring you. Like, the first step, if you want to do something, is to know the limitations, to know what you are facing. Now you know the things to consider. Now you can start using dynamic memory allocation, knowing what we should be careful about or what we should consider. And I think we have some time for a question, maybe. Then if there's no questions, and if not, then you can always catch me on the corridor. Then, thank you. Hello. Ah, okay.
There you go. It's like a gift for
okay.
donation.
Okay, okay.
So, and also you get the most important thing.
A
sticker.
Okay, thank you. Then it's like, thank you.